Okay, welcome everyone for participating in today's webinar on filtration. My name is Erkki Lamminen from DEKATI, and let's start with the presentation. Here are the contents. Very first, I'll very briefly talk about the DEKATI company and our products. We'll talk about filtration basics. What sort of things affect filtration, what sort of filters are there. And we'll discuss a little bit about filtration standards and what are the sort of standard methods of measuring filtration efficiency. Then we'll dive in more deeply into looking at our instrumentation. We'll talk about the ELPI Plus, or the electrical low pressure impactor. We'll take a look at what is a typical setup for ELPI Plus for basic filtration measurements. And we'll take a look at some application examples where the ELPI Plus has been used in filtration measurements, and specifically look at a few scientific studies where the ELPI Plus instrument has been applied. But first, briefly about the company. We are about 25 years old company from Tampere area. We are a spin-off company from Tampere University of Technology, Aerosol Physics Lab, and throughout the company's time, we have been focused on fine particle measurement instruments. So the development, manufacturing, and sales of those instruments. And our real core competence is in real-time fine particle size distribution and concentration measurements, and in sample conditioning technologies. We are located in Kangasala in Finland, and we export almost 95% of our sales through our distribution network. Just last year, we got the accreditation for ISO 9001, so we have a quality certificate. If we'll take a look at our product line briefly, we have a range of real-time instruments, namely the ELPI Plus, or the electrical low pressure impactor plus product family, which include the high temperature and the high resolution ELPI instruments. We'll be mainly talking about these instruments today because they are the most relevant for filter measurements. We have a couple of so-called real-time, more handheld instruments for more occupational health type work, for example. And we have a range of just gravimetric collection impactors for non-real-time collection of gravimetric samples with a little bit different cut points and flow rates. In addition to these, we have a wide range of sample conditioning devices, where our newest instrument is the eDiluter Pro instrument. These instruments are what we use when we want to measure from typically a combustion source, where there's a high temperature or high concentration of aerosol. We use these devices to dilute the aerosol down so we can then measure it with our measurement devices. But as said, today we'll focus on the electrical low pressure impactor product family in this presentation. We have quite a wide range of applications where our instruments are used. Of course, today we will be talking about filtration research, but our instruments are used in a wide range of other applications, including indoor-outdoor air quality, combustion optimization, nuclear safety studies, different automotive applications, including brake, tire wear, exhaust measurements, blow-by measurements, and so forth. And of course, occupational health measurements and general aerosol research, such as electronic nicotine delivery systems, bioaerosol generation, and just generation of aerosols. So there's quite a wide field, but today we'll focus on the filtration research. So if we talk about the filtration basics first, of course, what filtration is removal of particles from gas flow, or what we'll be covering today. And the quality of the filter is governed by two major points. One is, of course, the filtration efficiency, how many of the particles that enter into the filter penetrate the filter and come out through the other side. And of course, the pressure drop of the filter. So in an ideal world, an ideal filter would be such that it would have zero penetration of particles and have no pressure drop at all. So those are the qualities that are aimed at in a sort of an ideal filter or filtration system. There are quite a few different filter types. Of course, fiber filters like glass fiber filter or quartz fiber filter. These are most commonly known to us, of course, in our field in aerosol sampling, just pulling so-called filter samples and collecting the aerosol mass on the fiber filters. There are membrane filters like cellulose membranes, or for example, nucleopore membranes that can be used for both gas or liquid filtration, and tend to be very, very effective, and are used, for example, in HEPA capsules. These are, of course, also used quite frequently in aerosol sampling and creation of of gas flows with very low particulate concentrations. Then the most, say, widely used filters, maybe in industry and face masks and so forth, are the fabric filters, non-woven, woven filters, and in certain specific filters they use what is called Electret materials. So these are dielectric materials that then increase the collection efficiency of the filter while keeping the pressure drop low. We'll talk about electric filters in quite a few points in this presentation later on. Then, of course, there are other filters which are used for flue gas or exhaust gas filtration, like baghouse filters, which are, of course, fabric filters as well. We'll touch on electrostatic precipitation a little bit later on, and there are scrubbers, which are basically washing the gas, but maybe could be called filters as well. These will be covered specifically in another webinar later on this year, because it's a little bit too broad topic to cover all of these in a single presentation. So today we'll focus on more on the fabric filter filtration. So of course, in terms of filtration basics, it's the filtration is affected by multiple mechanisms. There's interception, where when a particle approaches a fiber in the filter, the flow path may run so that it simply comes into contact with the fiber, and when it comes into contact, it's generally collected from the gas flow. There's impaction, specifically for larger particles. So when a gas comes towards a fiber in a filter, the particle cannot follow the gas flow lines and instead impact onto the filter surface or the fiber surface. Then there's, of course, diffusion, where for smaller particles, now a lot smaller than the particles that impact, their flow path is affected by collisions with individual gas molecules, and their flow path is irregular, and they just by chance may come into contact with the fibers and get collected in that way. And of course, for a gas flow, it spends some time within the filter itself, and during that time, for very large particles, there's also the effect of gravitational settling within the filter itself, and by that means getting collected out of the gas flow. And one very important filtration mechanism is the electrostatic attraction, whereas if for example, the fiber itself carries an electric potential, it collects the particles more effectively. And as said, we'll talk about this more later on. And when we put all of these, I trust most of you have seen this picture. When these different mechanisms are put together, what happens is that the larger particles are collected via sedimentation, impaction, and interception, and the smaller particles are collected by diffusion. So what this causes is that for when we put all of the particle sizes here on the graph, we have typically sort of the most penetrating particle size through any filter around from 100 to 300 nanometers, because they are the least affected by any of these forces. They start not to be so much affected by diffusion and are not yet affected by interception and impaction. One thing to note here is that the electrical effects are not taken into account in this graph, and what the electrical effects can cause is that the most penetrating particle size is not anymore in the range of 100 to 300 nanometers, but we'll take a look at a few of those examples also later on. Now, if we talk about filtration standards in general, there are many standardization and guideline bodies like ISO, CEN, ASTM, VDI that have standards for different types of filters and for different classifications of filters. But generally speaking, there's a range of challenge aerosols that are used, not in all of the standards, but standard usually specifies one or few of these challenge aerosols. Most typically used are potassium chloride, so-called dust, which can be, for example, dolomite dust, oil droplets, or sodium chloride. And the most common measurement devices within the standards, so the standards say exactly which measurement device you should use or which technology. And most typically they are either optical particle spectrometers or photometers that are used in the standards to determine the filtration efficiency. Now, the benefit of these devices is the very wide dynamic range, which is of course needed since the challenge aerosol concentration before the filter is of course high, and if the filter is working properly, the concentration after the filter is fairly low. So a wide dynamic range is needed. However, for the optical devices, their output is dependent on the aerosol size distribution. So here's, I'm sorry, the graph is in Finnish language. This is the response of a photometer with different size particles and with different widths of the size distribution. And as you can see, the response curve, which is logarithmic, varies quite a bit depending on the size of the size of the particles or the shape of the size distribution. So this is of course also then affected by the fact that the filter itself changes the size distribution of the aerosols. The size distribution is not the same before the filter and after the filter, because the filter removal efficiency depends on size. So of course it's not directly relatable what is the concentration or the signal reported post-filter compared to pre-filter concentration. Also, that thing, since optical methods are used, they are not sensitive to particles depending on the laser that is used from 0.3 to 0.1 microns. So if there is higher penetration for smaller particles, you cannot detect it with the standard methods. So there might be a need post-COVID to maybe revise some of these standards to make them, for example, include also the nanoparticle size range. So the standard systems are there in place so that you could have repeatability when you compare different filter materials. However, if you're doing filter development, they are a little bit lacking in that sense, because most of these methods, once again, they don't measure the nanoparticle size range, and you get from most systems, you get just a single number of if it's increasing or decreasing the filtration efficiency. But it might be difficult based on just that result to know what is the cause of the increase or decrease in filtration efficiency. And of course, if you're doing things by the standards, you have a limited range of the challenge aerosols that you can use. So they are designed to somewhat mimic the real life conditions, but the results may not be representative of the actual conditions where the filters are used. For example, how the filters get loaded when it's filtering an aerosol, very different from the challenge aerosol. Or if there is Electret filter material used, how that is behaving depending on the challenge aerosol, especially if the challenge aerosol is charged as well. It might be better or worse in terms of collection efficiency. And of course, simple things like varying flow rates. Now, at this point, I'm going to stop at a few points in the presentation to, if you have any questions, please use the chat function in the system. But I'll stop for a couple more times in the presentation. But yeah, if you do have questions, please ask it in the chat. You can find it at least by pressing Alt-H. That should open the chat window and you can write your question there. I don't see anything in the chat at the moment, so we'll continue. We'll stop for a few more times during the presentation. So looking at the LP Plus product family, the LP Plus can measure number, mass, and lung deposited surface area, size distribution, and concentration in real time, up to 10 Hertz time resolution. The measurement size range is from 6 nanometers up to 10 microns in 14 size fractions. And with inversion calculation in the high resolution LP, we can increase that size classification up to 100 or 500 channels in that size range. Since it's a cascade impactor, we do collect the aerosol that we measure. We use sintered collection plates as default in the instrument, which allows us to make, as an example, from ambient air, we can measure up to 6 months, 24/7 continuously without any maintenance of the instrument. If you are familiar with the LP Plus using the analysis plates, you can think of the sintered plate sort of, if you had to do maybe clean the impactor once per week, with the sintered plates, you would need to clean it once per 5 or 6 months, basically. But of course, analysis plates are also available if you want to do post-analysis of the collected aerosol. It also has a very wide dynamic range. So we are measuring the base thing that we measure in the instrument is current with electrometers, and those have a range from few femtoamps up to about 500,000 femtoamps. So we have a very wide dynamic range in the measurement. We can also do charge per particle measurement. I'll cover this in a little bit later on, and what is the benefit of this. So we can, if the aerosol is pre-charged before it enters into the instrument, we can measure the charge distribution of the aerosol as well. But I'll talk about this a little bit later on. One key thing in the LP Plus is that the calculation routine is completely transparent. So we can give the calculation from the raw data that we measure to the final, whether it's number, mass, or LDSA size distribution and concentration. We can give the calculation routine to our customers. So it's a fully transparent calculation. There's no so to say black box features in the instrument. The operating principle of the LP Plus is shown here. We have a vacuum pump that draws a flow of 10 liters per minute through our measurement column, where the aerosol first enters into a corona charger. Corona sounds bad these days, but has nothing to do with COVID. So we have a corona charger where we have a tungsten needle to which we apply high voltage. This causes a corona discharge of ions, an ion plume in the charger, and the aerosol passes through this plume, and the particles get charged. Large particles get a lot of charge, and the small particles get less charge. After the aerosol has been charged, we have a trap field that removes the excess ions that we generate in the charger. After this, the charged aerosol moves into the cascade impactor. This cascade impactor size classifies the aerosol based on its aerodynamic size, and it does it so by accelerating the airflow in nozzles, and these nozzles direct the air stream or the air jet towards collection plate, which would typically be the sintered collection plate here. The air makes a sharp turn, and the particles with sufficient inertia, sufficient mass, they cannot follow this airflow. They impact and get collected on the plate. And in the next stage, we accelerate the flow a little bit more to collect smaller particles in the next plate. Now, as a difference to a conventional cascade impactor, the impactor stages are all electrically insulated from one another, and therefore we can connect with individual electrometers to each impactor stage and measure a current, which then is directly in relation to the concentration of aerosol. So when we know the size of the particles from the cascade impactor stage, and we know the charging efficiency for different size particles, we can directly calculate, for example, the number size distribution and concentration of an aerosol. The LP Plus, the calibration has, by the way, it's free of charge available through as a publication. Henna, you could actually throw the link up into the chat if you could. So if we would make a setup for the LP Plus for filtration measurements, we want to test filter materials, it's fairly straightforward. We use an aerosol generator that produces our challenge aerosol. After the aerosol generator, we have a HEPA filter here and so-called excess in or out. What this means is that if the aerosol generator, the ELPI draws 10 liters per minute. So if the aerosol generator generates more than 10 liters per minute, of course, the excess would come out. And quite typically, the aerosol generator generates less than 10 liters per minute. And in that case, the added air that we need to make up the 10 liters per minute is drawn through this HEPA filter. After this, it's quite convenient to have a use, for example, a dilution bridge. So what this does is that we have a HEPA filter and a needle valve. And if we close the needle valve completely, all of the sample goes through the HEPA filter. So then we have a very low concentration at this point. But when we start to open the needle valve, due to the pressure drop differences in the needle valve and the HEPA filter, more and more of the sample will go through the needle valve, and you can pretty much very easily control your challenge aerosol concentration to whatever level you like. I'm going to show you some results in a moment. I used the setup like this, and I used just a typical 47 millimeter filter holder that then had the test material for which I wanted to test the filtration efficiency for. And then just to have a simple three-way valve to select whether you are measuring through the filter holder or past, bypassing the filter holder. Now, one very important thing to, of course, test before the measurement is to make sure that you are getting representative results, meaning that have just a filter holder without the filter material and measure through the empty filter holder and through the bypass line, and make sure that you get the same result. So your measurement setup is not affecting your results. It would of course be preferable that the aerosol generator would produce a wide size distribution so that you can see the filtration efficiency in a wide size range. In my tests, I used 100% DHS in these measurements, which produces a fairly wide size distribution of aerosol. But basically with this setup, you can measure 10 seconds upstream, 10 seconds downstream, and in 20 seconds you have your filtration efficiency resolved with particle size. And of course, you might want to measure longer to see loading effects or whatever, but in terms of just quickly determining filtration efficiency for any material, it's fairly simple with a simple setup like this. So,
Erkki, we have
yes.
a question for you in the Q&A section.
Okay, thank you. Okay, we have a question whether the size fraction can be selected. Not with the cascade impactor. You cannot choose what those 14 size fractions are, but with the high resolution calculation, then when we can calculate up to 100 or 500 channels of size resolutions, then you do have then quite a lot more accurate measurement of particle size over that size range. We'll probably have another webinar this year about just the high resolution measurement itself. Or we can send you more information about that. But going through the inversion calculation takes a little bit too long to go over here, but it's fully documented and fully open how it's done as well. So that is available as information. So if we take a look at the results, so this was actually done with the high resolution ELPI Plus, and we measured the filtration efficiency at a fairly wide size range. what we found out, that has been also found out in other studies, is that the most penetrating particle size is not always at from 100 to 300 nanometers. So what we are looking at here as results, we have the penetration through the filter. So it would be desired to have this as low as possible. And we have the particle size range roughly from 30 nanometers to about 1 micron here. These fabric 1, 2, 3, 4, 5 are just household fabrics. I did these measurements out of interest, basically trying to see whether I could guess which fabric would be the most optimal in filtering aerosol. And as you can see, most of these fabrics do not do particularly well. Fabric number 1, I don't know, or was it 5 that I guessed would be the best was actually, so this was a much thicker fabric than the others and with a higher flow resistance. So it was quite expected for it to have the best filtration efficiency out of these household fabrics. And then I loaded all of these 5 different fabrics on top of each other, and then the filtration efficiency fairly well comes as a sum of the filtration efficiencies of the separate fabrics. But of course, that type of a face mask would be fairly difficult to breathe through with 5 layers. Then we have result from an FFP2 face mask, which clearly fulfills the requirements of the FFP2 regulation. This was actually already used face mask. This fulfills the requirements of the regulation, but it does have higher penetration for smaller particles, notably at around 60 nanometers. And this has been found also in other studies to be the case. So these, what causes this is that these face masks use Electret materials that increase the filtration efficiency, especially for the larger sizes, with a reduction then in the pressure drop across the filter. But it's not as strong here, so we can see penetration around 50, 60 nanometers. We have a mode there, and there are studies that show, due to the fact that the FFP2 masks have Electret properties, if you, for example, dip them in alcohol, in isopropyl alcohol, it can quite dramatically reduce the filtration efficiency because it loses the Electret properties. I want to share with you another result, which was more a troubling result during 2020 measurements. This is another measurement of 3M FFP that fulfills the requirements of the regulation. And then there was one that was marked both N95 and FFP2 markings. There's a Chinese made mask where it had a curious performance where very quickly during loading, the filtration efficiency started to shift. So most of these other filters, especially for the FFP2 filter, the filtration efficiency stays the same, at least for minutes when you are loading it. So it does not change in really, or doesn't seem to change in use. But for this face mask, I could see immediately when I started to challenge it with the challenge aerosol that the penetration started to change. So here's the example of the penetration curve in the beginning, and after 5 minutes of loading, it has already shifted quite a bit with more penetration for the larger particles and a little bit less penetration for the smaller particles. Now, this is probably caused by, of course, the effect of the DHS liquid aerosol causing some change in the filtration material, but it was not very nice to see that some of the masks which are branded as N95 or as FFP2 masks are clearly not as efficient as they should be.
We have another question about the generation of the particles in the setup.
Let me see if I can get that open. Here we go. Okay, so we have a question about the generating the DHS particles and controlling parameters such as concentration, size, stability. That's a very good question and important one. I was using a Topaz generator, so from a German company Topaz. They have a portable aerosol generator that's quite nice, easy, simple use, doesn't need an air source. So I use that as the aerosol source. Definitely the stability is of course very important because if you have any drift, that's going to directly affect your filter test results. The concentration can be adjusted, for example, by using a dilution bridge or any other type of diluter, or one other way would be to simply add clean air to the system and then allow an exhaust where the sample that is not used is exhausted. But I found, at least for my quick measurements, the dilution bridge was very simple and easy to put together. Yeah, the size of the generated aerosol, there are of course you can use different sources. So this was just a nebulizer basically, but you can use evaporator condenser generators to generate smaller aerosols, or then use different pre-cuts, for example, to eliminate some of the larger sizes if you don't want those, or if you want to go really into selecting a single particle size, for example, use a DMA to select if you want to really measure with monodispersed particle sizes. So that's one option, but the concentration is fairly straightforward. The stability then depends on, of course, your aerosol generator itself, and that's one thing that you should definitely also check. It needs to be a stable source, because otherwise that's going to influence all of your results. Then one more point about particle charge measurements, which I mentioned briefly before. So what we can also do with the LP Plus instrument is we can measure the particle charge. So typically when we want to measure the number, mass, size distribution of an aerosol, we have our own charger on. So we have a known charge on the aerosol, and we do the measurement, do the calculation, and we come up, for example, with a number size distribution of a particular aerosol. What we can also do is we can turn our charger off, and then if the aerosol is already charged, then we can measure that charge level again with the electrometers, and the electrometers can measure both positive and negative charges. So in this case, for example, the aerosol would have been negatively charged. And with that information, with both size and the concentration and the pre-existing charge on the particles, we can calculate how many, for example, elementary charges are there on top of the different size particles. And where this information can be used is a couple of things. For example, to measure the charge level of your challenge aerosol. So it would be preferable that your challenge aerosol is neutral. So with the ELPI, with the charger off, you get very little or no signal. Unless the purpose is specifically to study the effect of a charged aerosol on the filtration efficiency, because it will have an effect on the filtration efficiency. If your aerosol is charged, it very usually is collected more effectively by the filter. The other thing you can do with the this charge measurement is measure the charging efficiency of another charger. So as I said, I'll come briefly to electrostatic precipitators in this presentation, but an ESP works so that it charges the aerosol and collects all the particles, or tries to collect all the particles from the gas flows. But some of the particles come out of the electrostatic precipitators, and those particles usually carry a charge. So with the ELPI, in terms of ESPs or any filtration system that uses aerosol charging as well, we can measure how effective the charging mechanism inside the filter is, separate from the collection efficiency of the filter that uses charging. Let's see, there's a okay. We have a question how to prevent Corona charger from producing its own aerosol. We haven't for the charger that we use with the voltages and the current that we use in our Corona charger, we haven't seen aerosol generation events in our Corona charger. So we use about 3.5 kilovolts and 1 microampere. So the power of the electrical power is fairly low in our Corona charger itself. Pretty much the only way to, if you feed certain gases, like I think SO2 in very high concentrations into the Corona charger, you might see some particle generation, but otherwise than that, we haven't seen aerosol generation from our Corona charger. Maybe partly because it's a fairly low power Corona that we have in our instrument. It's time for questions, and then we'll start with the application examples. Okay, I think I'll move forward. So first example, coming from the making filters through electrospinning out of different materials. So electrospinning is a fiber production method where it uses electric force to draw threads from different solutions, where the thread is then ending up and collecting on the collector. It's similar to electrospraying, but instead of producing droplets, it produces a thread. So with this method, in this study where you can see the reference here, a very large number of different filter materials were generated. So here's the measurement setup. There's the generation of the challenge aerosol and the dilution to adjust the challenge aerosol concentration. As you can see, it's a different setup, not using a dilution bridge, but larger gas flows here, but it doesn't, whatever gets you the suitable concentration for your measurements. Then there's a charge equalizer. So I said if the generated aerosol has a charge, that affects the collection efficiency on the filter. So the aerosol was neutralized here, and then we had the test filter and measurements before and after the filter with the ELPI Plus. Here are some of the results. As you can see, fairly high filtration efficiencies with some of the materials. And as you can see, the ELPI can determine between fairly low changes in filtration efficiency. But the study was very comprehensive. So there was a very wide number of filters and different amounts of combinations of filters measured, and very interesting results, seeing of course the pressure drop is inversely related to filtration efficiency, which is expected. So with a lower pressure drop, you get a lower filtration efficiency. No, that's directly related to filtration efficiency. So with a lower pressure drop, you're going to get less filtration. But this ratio varies with material, of course. So the idea is to find those filtration materials where you have the lowest pressure drop with the highest filtration efficiency. Very interestingly as well, of course, the most penetrating particle size varies with material. It of course varies also with flow rate and other factors, but it's also material dependent. We have a couple of more questions. Besides quality factor, there is dust capacity. Yes. Protocols and standards to measure it. I'm going to say probably there are. I've read quite a few filter standards. There are probably some loading. There's some requirements for loading of the filters, at least in some of those standards, but I cannot name them off the top of my head. And this is another very important point, is the fact that when we have different materials and different pressure drops and filtration efficiencies, these are all how they behave in the long run in the actual use is of course then also dependent on the challenge aerosol that is used. So if it has a lot of nanoparticles or it has a lot of coarse particles, those will load the filter differently. So and for example, with nanoparticles, even if the mass is low, but if it clogs up the filter more efficiently, then your pressure drop might go up much more quickly than what you would expect. I think there's another. Okay, we'll take the rest of the questions in the end, since we are pretty far along on the time, so I'm trying not to go too much over the hour. We'll move on to the next example. In this article, what they did was they made Electret air filters that we discussed before already on this presentation. And the idea was to check the effect of adding titanium oxide to melt-blown filter materials. and to do this with different electric field intensities during the weaving process itself. And here are the results. So the results are here with 1, 2, 3, and 4 weight % of the titanium dioxide. And then if it's weaved at different electric field intensities, 1.5, 2.0, and 2.5 kilovolts. So what we can see here is that, first of all, the 3 weight % and the highest weaving voltage that was used gives the best filtration efficiency here. There is strangely high penetration for large particles, which I think may be related to the, it's not stated in these slides, but the filter had very low pressure drop, which is of course good for the filter. And it looks to me at least like that the filter collection efficiency with sedimentation, impacts, and interception was fairly low before a sufficient electric field was used in the weaving process. So the electrical effects became strong enough to increase the collection efficiency of the filter. Of course, with electric filters, the other question is also the longevity of the electrical effect of the Electret filter. Then the last example I have is from the nuclear safety side. So metal cutting, which is of course a widely used process in nuclear power plant decommissioning, it produces, as one could expect, a wide size range of aerosols. So typically HEPA filters are used to protect workers, but how does filtration efficiency change over time? And this is of course very, very important in the sense that in a nuclear power plant decommissioning, the risk is of course that the metal that is being cut actually releases radioactive material during the cutting process. So this next quote is from the article itself. It's fairly long, but I'm going to go through it because it sort of highlights some of the things I've been trying to highlight myself in this presentation. So states that several studies have been conducted for evaluating factors affecting filter efficiency. However, most studies have been conducted using conventional aerosol generators, and aerosols that occur during metal cutting have not been addressed significantly. In addition, many studies have not fully considered the distribution of particle sizes for the efficiency of filters, although it's significant to understand the fraction of aerosols smaller than 0.1 microns for reducing internal radiation dose. And actually, quite interestingly, what they found was that the filtration efficiency for this case, it drops as the filter is reused. So the filtration time, this 1, 5, 10, 15, 20, these are not minutes, these are actual cutting events. So this is the first sort of cutting event. Then it's after 5 times of use, 10, 15, and 20. And what we see here is consistently with increased use of the same filter, the efficiency drops from close to 100% down to about 93% after 20 times of use for in roughly 1 to 2 micron size range. So typically we expect filter efficiency to go up as it's getting loaded with aerosol. But in this case, it's dropping, and this is maybe due to the change in the electric properties of the filter if the aerosol that is produced during the metal cutting is actually charged itself. So it might sort of neutralize some of the electret properties, or something else is happening. Anyway, the filtration efficiency drops with repeated uses of the HEPA filter. So these are my conclusions now, and then we'll take a look at the rest of the questions. So first of all, what we went through, the efficiency of filtration is dependent on multiple factors: material, filter material, flow through the filter, loading, humidity, and the longevity of the electric material or its electrical properties. And the standard measurement methods, while they are very good when you want to just compare one material, filter material, to another, and to make sure you have reproducible results, they do not really provide sufficient information to characterize filter performance in all real-life conditions. So then, why to use the ELPI Plus for filtration measurements? Of course, the dynamic range that I talked about, with the signals that the raw signals that we measure, we can measure up to 99.9975% filtration efficiency with that current ratio from 10 femtoamps to 400,000 femtoamps. We have a wide size range, all the way down to 6 nanometers. So in the case that the most penetrating particle size is below 0.1 microns, we have no problem in measuring that. Of course, we have real-time measurements, so you can see the effect of filter loading on filtration efficiency and see that size-wise effect as well. Said the data is transparent, raw data is available, and after you have measured for those few months and you do need to clean the unit, it's very straightforward. It's all basically stainless steel, so it's very straightforward to clean it. And then the possibility to run charge measurement to do studies both of electric filter behavior or indeed the charging efficiency of filters that use charging themselves, or checking the challenge aerosol charge level in filtration efficiency studies. So basically, the ELPI is well suited for filter behavior studies in the actual real life conditions. So I want to thank all of you, and now I'll check further questions. Does the particle chemical composition have any influence on the ELPI, I guess the ELPI measurement? No, the particle chemical composition itself, since the charging that we use in the instrument is based on diffusion charging. So the ions in our charger diffuse onto the particle surface. So the particle doesn't have any real effect on the charging process. And then of course the size classification is based on aerodynamic size of the particles. So it's almost independent of the particle chemical composition on the ELPI measurement. Does the frequency of cleaning required for the ELPI Plus correspond to a particular mass loading on the impactor plates? Yeah, so roughly, if we talk about analysis plates, and then the sintered plates, which are used as a default. It depends a little bit on the particle material itself, but roughly with the analysis plates, you could collect about 1 milligram per stage. And with the sintered collection plates, maybe 30 to 50 times the amount that you would collect on the analysis plates. So 30 to 50 milligrams of material per plate. Let's see. We have a question of, does the corona charge degrade with time due to particle deposition on electrodes? The corona itself, in order to keep the corona charger stable, what we do is we keep the charging current stable. So the current is 1 microamps always, which means that we have roughly the same amount of ions always in the space where the aerosol passes through the ion plume. Of course, over time, some particles will collect on the charger walls and cause a little bit of an insulative layer. But as we keep the current stable, the voltage then automatically increases to keep that current at 1 microamps. So there's the same amount of ions and we get the same charging efficiency for the aerosol. Of course, from time to time, you do need to open up the charger. It's, once again, it's basically a stainless steel block, and quickly wipe the insides of the charger. But this is something you don't need to do very frequently. We have a question as each filter or the collection plate retains particles with different size. What is the typical duration of one measurement? If the question is how quickly you get, the real-time measurement is instantaneous. And if you're talking about how long we can measure with the instrument, it of course depends on the concentration. But as said before, if we would talk about, let's say, ambient measurements, you could measure for roughly 6 months in the ambient. So it's you can measure for a really long time without cleaning the instrument. Let's see. We have quite a lot of questions from one participant, and we will. There's a lot of questions here, and I think we'll answer those separately via email, because otherwise it would take a very long time. We have a question on how sensitive are the internal electronics to radiation exposure. Our systems have been widely used in nuclear safety studies. However, we haven't had an instrument returned to us due to problems with degradation of the internal electronics, or indeed some faulty signals due to radiation exposure. However, I have to say that most of the studies that are related to nuclear safety are so-called simulation studies, where the so-called radioactive aerosol is actually simulated by some other aerosol that is not radioactive, because if you use radioactive materials, your of course the measurement setup and all the safety features are increased by more than tenfold. But we haven't seen any data of that, and these have been widely used. But it's also with the nuclear safety side, I have to say that we do see their publications, but otherwise it's a field where there's fairly limited information that comes out. We have a question on tested efficiency on membranes like PTFE membranes, and evaluated most penetrating particle size less than 0.1 micro. We have not done that. I believe the efficiency should be fairly high, but we could. The only thing stopping at the moment doing measurements at our lab is that we try to reduce the number of people in the office, of course, but that could be done. I don't have data of that from the top of my head, but would be fairly, of course, a simple measurement to do. I don't see, let's see, I don't see at the moment. We have a couple of other questions that I missed at earlier on. We have a question on the maximum resolution of the instrument. So as said, the high resolution ELPI has the size range or has 500 channels within the size range of from 6 nanometers up to 10 microns. We have done studies on, it's of course not, you don't get the same size resolution as with a DMA or an SMPS, but the ELPI Plus has the best, it's the best real-time instrument for this size range for the size resolution. We have a question on application examples of measurements made with the instrument on HEPA and ULPA filters. I don't have those at the moment. This is something I'm planning to do myself in the office once I get back there for the HEPA capsules and see, because I do know that we can measure the filtration efficiency, since as I showed you the setup, when we have the dilution bridge, we do see concentration coming past the HEPA filter. So there are measurable concentrations measurable after the HEPA capsule. So that I'm planning to do that in the future. Let's see, I missed. Okay, we had a question on the dust capacity protocols, but there was then a connection problem. So I do believe that there are some loading protocols in some of the standards, but I can't off the top of my head note to them at this time. But this is a very important question in the sense that there are certain aerosols that are used in the standards, but then in real life, as said, if the aerosol, for example, contains a lot of nanoparticles, it might load up or clog up the filter much more quickly than if the loading aerosol is only consisting of coarse particles. So it's definitely an important field of study. And I think I've answered everything that I see here. Can you let me know, Henna, if you think I've missed some question?
I think you answered everything. It was very nice to see so many questions during this webinar, and we will also send you the presentation after this via email. And if you have any further questions that you want to ask from Erkki or from Dekati, then the best way to reach Erkki or anyone else in our company is to send an email to sales@dekati.fi. So please feel free to send any further questions there. And thank you from my side for participating, and thank you, Erkki, for a really interesting presentation.
Thanks also from my side, and thank you all for participating. And I did recognize quite a few familiar names, so hopefully we'll be seeing each other in the real world in the future soon. But thank you very much, and until next time.